Here are the Module 5 notes, examining relationships in linear regression. This is pages 5 and 6. Again, a definition, we are starting with our linear correlation coefficient. It just measures the strength, the closer it is to 1 or negative 1, and the direction, whether it's positive or negative. Of a linear relationship. Okay, positive, negative. So we got how close to the absolute value of 1, so 1 or negative 1. Okay. Here is our equation for the correlation coefficient, and I'm sure you've read ahead that says you will never have to compute this. This is one of the nice things in the reworked statistics. The important thing is that you understand what the correlation coefficient means, what it tells you, and not necessarily how to crank it out. Some of this we've seen before. Sigma means sum. It means we're adding things together. The x sub I, y sub I is an individual data point. Then our x bar and our y bar would be the means for our x's and our y's, and the s sub x and s sub y would be our standard deviations. Okay, again, notice we divide by that n minus 1, one less than the sample size. So a couple of properties here that are important to remember, just so you don't get something weird. Linear correlation coefficient is always between negative 1 and 1. If R is 1, it's a perfect positive linear relationship, and negative 1 is a perfect negative. If real-world data is giving you a 1 or negative 1, then we probably have an issue. Now, there are some situations where you will see that, but typically not real-world data. Okay. For the closer to 1 or negative 1, the more evidence there is for a linear relationship. If it's close to 0, it suggests little or no linear relationships. And 6, that correlation coefficient is going to be affected by outliers. Okay, one more set of pictures here with the correlations coefficients underneath. This is one of those things you just gotta kind of see over and over again. So I kind of threw in all the pictures I found. Okay, so let's talk about examining correlation coefficients and how we use this sentence, or interpreting correlation coefficients. So if R is negative 1, okay, again, we're talking about number of absences and attendance grade. Okay, so our explanatory variable is number of absences. The response variable is the attendance grade. We have got an R of negative 1. There is a perfect negative relationship, perfect negative linear correlation between the number of absences and the attendance grade. That makes sense. The attendance grade is based on absences. It should work the same for every single person. There should be a perfect correlation there. B, we've got an R of negative 0.25 for the numbers of hours watching TV and GPA. Our explanatory variable is number of hours watching TV. Our response variable is our grade point average. We interpret R as a week negative linear correlation. And these words are going to be important as you look at project 1. You are going to describe the relationship you have between your two variables. So C, we've got R equals 0.98 for square footage of house and selling price of house. So our explanatory variable is our square footage of a house, and the response variable is the selling price of the same house. We interpret R this way. There is a strong 0.98 is very close to 1. It's not perfect. Only 1 and -1 are perfect. But this is a really strong positive linear correlation between square footage of a house and selling price of a house. D, our last example here, R is 0.75 for outside temperature and ice cream sales. So our explanatory variable is the outside temperature. Our response is ice cream sales. So if I owned an ice cream truck and I wanted to be able to order accurately, I didn't want a whole lot of ice cream I had to store every night, I would see if I could find some sort of relationship between temperature and possible sales. So at 0.75, this is a moderate, positive, because it is a positive 0.75, linear correlation.